Hello, everyone. My name is Yu Mingrui. It's a great honor for me to present our work, Generalizable Whole-Body Global Manipulation of Deformable Linear Objects by Dual-Arm Robot in 3D Constrained Environments. Deformable linear objects, which are called DLOs in short, refer to the deformed objects in one-dimensional shape, such as ropes and cables. For practical applications of DL manipulation, it is necessary to consider the constraints from the obstacles and unbodies. Our last year's work proposes a cost-to-find framework for DLO manipulation with whole-body obstacle avoidance, which combines both the global planning and local control. The global planning is to plan a course path to efficiently find a global feasible solution, and the local controller follows the guiding path and reacts to the real-time feedback to improve the task accuracy. The achieved tasks were relatively simple, so we would like to further explore whether we can deal with more complicated environments and tasks. This work is a significant extension of our previous work. We consider more practical and complex 3D tasks and achieve much better performance, such as 100% success rates of both the planning and executions. Compared with our previous work, the key improvements include employing a new DLO engine model, optimizing the planning algorithm, and extending the controller to a long horizon MPC. We exploit the discrete elastic rod model at the DLO energy model for global planning. Compared with mass spring model we previously used, this model additionally accounts for the twisting and gravity effects. We optimize the whole body global planning algorithm to highly improve the planning success rate, efficiency, and path qualities. We formulate the local controller as a nonlinear non-horizon MPC with hard constraints for obstacle avoidance. Compared with the artificial potential methods we previously used, it works much better in narrow spaces and achieves more smooth tracking control. Our approach achieves 100% planning and execution success rates on the most complicated simulated tasks, and the average planning time cost is less than 10 seconds. We test our approach on 5 different DLOs from stiff to soft in the real world. Our approach can robustly achieve such a real-world complicated task, which is much more challenging than the tasks in the previous work. The comparison between our closed-loop framework and the open-loop manner demonstrate that the controller can well compensate for the planning errors owing to the model simplifications during planning. Here are some cases of potential applications. The first case is moving and embedding the DLO into the grooves. The second case is moving and inserting the DLO ends into the holes. In conclusion, we propose a complementary framework that efficiently and accurately accomplishes these high-dimensional and highly constrained tasks, and also effectively generalizes to various DLOs. Thank you for your listening.